Hi everyone, welcome to this new lecture Fluid Mechanics. In this lecture, we'll discuss a concept of separation of boundary layer. In our last lecture, we already have discussed regarding the boundary layer theory concept. There we have discussed how this boundary layer formed and what is the main region of boundary layer formations and what is the application of boundary layer. Now we'll see what is the region of separation of boundary layer and also what are the types of boundary layer formations are there. So to understand this boundary layer, separation of boundary layer, we have taken, you can see here, the number of velocities are given, like, the fluid which is flowing, it is given in different layers. And this U is indicating here the free stream velocity. So in the last lecture also I told you, U is nothing but free stream velocity. The fluid is flowing with a free stream velocity, that is capital U. And this is the first point. So we need to consider a fluid flow with a velocity of u and which is flowing over a smooth thin plate. So this is the plate what we have considered. So this one we can see, this is the plate. This is the thin plate is there, and the fluid is supposed to be flows over this thin plate. Okay, so this one is taken a plate, and the fluid is flowing over the smooth thin plate. And this plate need to be considered. It should be a thin plate is considered, and the fluid is supposed to be flows over this. And this is actually, it should be kept in a flat and parallel. It should be flat and parallel to the direction of fluid flow. Parallel to the direction of fluid flow. So you can see the fluid flow directions I have given. So that is same in the direction also, it should be kept here. Now let's consider the fluid flow. With here, the fluid flow is having a zero pressure gradient, okay, at the side of the plate. Okay, so you can see here, this is a pressure gradient zero means here we can consider the stationary plate is there. That means the plate is placed with a stationary condition. So that is one considerations. And the next is the velocity of the fluid on the surface of the plate. The velocity of the fluid on the surface of the plate, velocity of the plate, we can consider here small u. Let us consider a small u. So velocity of fluid on the surface of the plate, that will be actually need to be considered. The fluid surface of plate, it should be equal to the velocity of plate. What I mean to say, that means the velocity of the fluid at this condition, at this plate near to the surface of the plate, should be equal to the velocity of the plate. But here if you see, the plate we have taken as a stationary or fixed. So the plate is fixed means obviously there will be no movement in the plate. So here, though the plate is considered as a stationary, already told you the plate is considered as stationary. So the velocity of the fluid, also of the surface of the plate will be equal to zero. That means there is no fluid, there is no movement of the fluid near to the surface of the plate. Okay, but if you see, if you consider from this from this point here, at this point it is zero. But if you consider some distance from this plate, like from this leading edge, then we can see some kind of movement of the velocity. Some distance if you consider from the A of the plate, okay, like if you go some distance from here, you can see some kind of velocity is there. Some kind of velocity of the fluid is identified having a certain velocity. So we can get some velocity value here. We can write capital U or same U we can consider here on behalf of V. Now here we can see there is a change in velocity of layer to layer that we have discussed in our last lecture. Here also I'll show you how this layer formation should be there. Suppose here I have taken a plate here, and when the fluid strikes here, okay, after striking here, what will happen? Few liquids will be close in contact with this plate. Okay, so due to this, adhesive force between this solid and the fluid particle, the velocity of this point will be zero. So at this point it will be zero. But next to the surface of this layer, Okay, the slightly the velocity will be increased because their adhesive forces will be weaker and the cohesive forces of the fluid will be increased. That's why here you can get some kind of fluid force. So here if you see slowly it will be like, it will be increasing more. So at this what now, suppose let me consider the plate here. So here we'll get this kind of condition. Now at this region, the small u will be equal to capital U or U infinite, which is known as free stream velocity at this point. Similarly, at this region, again I'll draw some velocity line. So here I'll get at this point, I can see that local velocity will be equal to the here free stream velocity. Similarly, here also, we can get like this. Yeah, at this region we are getting some similarity between this. So like that, if I join all these points, so I'll get a curve like this. And that is a boundary layer actually. So this is our boundary layer over the plate. Okay. Similarly, what we have discussed in our last lecture, boundary layer over a stone we have discussed. Now here we need to divide this boundary layer zones, or you can say different types of boundary layers. So that I'll show you. Now here, as we are discussing here, the distance from this surface, the velocity increasing. Now you can see the velocity increasing, but there is a variation of velocity is there. So the variation of velocity, that is actually nothing but du by dy, which is known as velocity gradient. Already I told you previously also, this is velocity gradient. And the velocity gradient is created near to the surface of the plate. We can see near to the surface of the plate, the velocity gradient is created. How it is, like, here one layer, then another layer, then another layer. Like that, we'll get lot of layers. And if you draw in the vertical here, then you can get a form like this. Okay, so everywhere will form that velocity layer will be formed like this. Now this velocity gradient will be formed near to the surface of the plate. But this velocity gradient actually, this will develop a shear resistance. So the shear resistance is nothing but we have seen in the shear stress. So due to this shear resistance, the fluid flow started slow down. Due to this shear resistance, the fluid flow started slow down. Now, next what I can say, the fluid of that fluid which is having the uniform velocity or that free stream velocity u, so this is also going to be slowed down over the nearer area of the plate. Okay, so that's why we can get a increment in the fluid flow velocity, like local velocities are increasing here. Slowly the local velocities are increasing, and it is taking some time to reach the free stream velocity. So the boundary layer region increases. You can see this boundary layer region increases because of the slowdown of this fluid, or you can say retarded fluid. Continuously it is retarding. That means continuously it is slowing down according to the length. That's why this boundary layer region increases. Which region? This is the boundary layer region, what I told you. This one. This increases. Now near to the leading edge, you can see the surface plate, we can see the thickness is very small. We can see the thickness is very small. So the flow in the near to the boundary layer, we can see is laminar here. Near to the plate, you can see is very low, and the flow is low means the flow can be considered for the laminar. But how we can say this is a laminar flow? So I'll tell you one reason, that I'll tell you one formula. By that we can identify the laminar flow. Actually, the layer of the fluid you can see here, the layer of the fluid at this region, this layer is called actually laminar boundary layer. So as we can see, the laminar flow is developed here at this region, and the layer which is constructed at this region, that is called laminar boundary layer. So how we can see this is or how we can define, or how we can calculate up to what region that laminar boundary layer formation happened. So that is actually based on the Reynolds number value. So for the plate, the Reynolds number is given 5 into 10 to the power 5. So this is the value, Reynolds number value for a plate. And we know that the Reynolds number formula is, we know that we can write the Reynolds number equal to, either we can write, previously we have written rho VD by mu. Now here diameter is not there, so you need to write rho VL by mu, or we can write rho Vx by mu, or we can write Vx by nu. So V equal to, or you can write U also. So here let's write U. So we can see U is the velocity that we know, and X is the distance. X is the distance from the plate. Distance from the plate. From the edge, you can say. From the edge. And nu equal to, we know that this is kinematic viscosity. So what it means, so from this A point, if you see up to the B point, this is the value of X. So now here if you put the value of RE equal to how much? That is 5 into 10 to the power 5. So this equal to, we can write U into X by nu. Now in this term, if you see, the X value is unknown. If U and nu are given, that means velocity and kinematic viscosity of the fluid is given, then we can calculate the X value. Then we can say up to what distance that laminar boundary layer exists, and that is called actually laminar zone. Okay, that is called laminar zone. So based on this X value, we can calculate the, we can identify which is the laminar boundary layer, you can say. Then the next to that laminar boundary layer, you can see a few slight zone is there here. That is actually transition zone. This is actually transition zone. That means that fluid converting from laminar to turbulent actually. So in the turbulent zone also, how we can identify? When the turbulent boundary layer, what we can say, when the length or distance is more than the distance of X, so and that will be calculated by this, by applying this equation. So then we can say from that region it is called turbulent boundary layer. So actually this zone will be very less. This transition layer will be very less, and this zone also very less, that is BC zone. So this is very less here, and from, like, you know, this point actually it's transiting from laminar to turbulent zone. So that will be mostly, it won't be identified. Once it cross this length X, then from there the laminar boundary layer started. Okay, and this zone is called turbulent zone. This is called turbulent zone, and this zone is the small zone is there, that is transition zone, which is defined by the distance BC point. Okay, now here we can see the turbulent boundary layer here. Now one more point is there, that is laminar sublayer. This is another one important part. This is laminar sublayer, which is created in the turbulent boundary layer region. So how it is created, I'll tell you this one. So just have a look on this surface. This is the surface which is created. So I'll show you here. So actually that laminar sublayer is nothing but, this is also, let me write laminar sublayer. So this is also called as a viscous sublayer. This is also called as viscous sublayer. Why it is called viscous sublayer? Here the viscous force effect is more, or the viscous effect is more at that region, so that it is called viscous sublayer also. So this region, actually in this region your viscous force will be more dominated to that, and there no slip will be occurs. So no slip means, we know that what is the meaning of no slip occurs. No slip is your velocity will be zero at that region. Velocity will be region. That means there is layer formations will be there in that near to the boundary. Okay, and there will be no movement of this fluid. Okay, there is no movement of the fluid will be there. So that's why here no slip will be occurred there in this. That means the fluid particles and near to the surface. Okay, so that will be very smooth. That means the flow will be very smooth in this condition, and that will be parallel flow will be there. Okay, and though it is a turbulent region, but at this layer we can see, okay, there will be no movement of this fluid flow, because some layer formations will be there, and in that region, that is velocity will be 0 at that point, because we used to consider the no slip condition near to the surface. And that is one more point. And along with that also, we can write an equation for this, like the shear stress, we know that tau, the shear stress, we can write tau equal to mu into du by dy. This is one equation. So the shear stress in the laminar sublayer actually will be constant. The shear stress for the laminar sublayer will be constant, and that will be equal to the boundary shear stress. So that is, boundary shear stress is nothing but tau naught. So boundary stress also we can write, this is like mu into du by dy. And what is the distance? Now y equal to 0. So y equal to 0 means we can write this is du by dy equal to mu by y, we can write. For the linear variations, that means the variation is very low, or equal variations will be there. So this one we can write mu into u by y. This is tau naught. Okay. So though this laminar sublayer formed here, but this is this is turbulent flow is there. Here we can get a apogeal flows are there, a lot of flows will be there, but a layer will be formed at this region near to the surface vicinity. There will be the no slip conditions will be there. That means no velocity will be there. So this is about the laminar sublayer, and this all the concepts regarding the separation of boundary layers, like how the boundary layers are different. And here, as I told you, we have three, like not three exactly, mostly used to consider two only. One is laminar boundary layer, another one is turbulent boundary layer. Okay, so laminar, so main formula is this one. Based on that, we can calculate laminar boundary layer, what is the laminar zone and what is the turbulent zone. And this transition zone is only to just to convert this laminar zone to turbulent zone. It depends upon the value. So just keep this value in mind, R equal to 5 into 10 to the power 5. Remaining all are simple. And another one concept, that is laminar sublayer, which is created near to the surface. That's it. So I hope you understand this concept. Still, if you are having any kind of doubt regarding this, you can give a comment on the comment box. Thank you.